Welcome to AI Frontiers, the podcast that brings you comprehensive analysis of cutting-edge developments in artificial intelligence research. Today's episode focuses on the reasoning revolution, synthesizing 11 papers published on May 21, 2025. This special edition explores recent breakthroughs in computer science, artificial intelligence, commonly known as cs.AI. This field represents the core of AI research, focusing on developing systems that can perceive their environment, reason about complex problems, learn from experience, and take actions that maximize their chances of achieving specific goals. The papers we'll analyze showcase the remarkable diversity and rapid advancement of artificial intelligence. As AI systems become increasingly integrated into our daily lives, from virtual assistants and recommendation systems to autonomous vehicles and medical diagnostics, the foundational research in this domain shapes not only technological innovation but also economic development, social structures, and ethical frameworks for human-machine interaction. Join us as we begin our journey through the frontiers of artificial intelligence. In today's episode, we'll examine 11 cutting-edge papers in artificial intelligence, all published on May 21, 2025. Our analysis will identify 5 dominant research themes that are currently shaping the field, highlighting groundbreaking results and methodological innovations that represent significant advances. We'll analyze the implications these developments have for future AI research and applications, providing a comprehensive synthesis of current research priorities and challenges. This exploration will give listeners a clear understanding of where AI research stands today and where it's headed tomorrow. The papers we'll discuss span multiple subfields, reflecting the interdisciplinary nature of modern AI research and its increasing complexity. From improvements in large language models to advances in formal verification methods, these papers collectively paint a picture of a field that continues to evolve rapidly, pushing the boundaries of what artificial intelligence can achieve. Before diving into specific research themes, let's establish the current landscape of artificial intelligence. AI is a highly interdisciplinary field spanning multiple domains including machine learning, reasoning, knowledge representation, planning, natural language processing, computer vision, and robotics. These subfields often overlap and interact, creating a rich ecosystem that drives innovation. The current AI landscape is characterized by several important trends. First, there's a growing focus on interpretability, safety, and value alignment, ensuring AI systems not only perform well but do so in ways that are understandable, safe, and aligned with human values. Second, we're seeing increasing integration of formal methods with learning-based approaches, combining the mathematical rigor of verification techniques with the flexibility and power of machine learning. Third, there's a trend toward multi-agent systems for tackling complex problems through collaboration between specialized AI components. Finally, there's a strong emphasis on bridging theoretical advances with real-world applications, ensuring that AI research translates into practical benefits across various domains. The first major theme emerging from these papers is advanced reasoning in language models, with researchers focusing on making AI think more efficiently and transparently. Zhang and colleagues introduce a framework called adaptive self-recovery reasoning, which enables models to allocate reasoning effort according to problem difficulty. This approach recognizes that not all problems require the same depth of reasoning, and by adaptively adjusting the reasoning process, models can become more efficient without sacrificing accuracy. In a related vein, Zhu and colleagues conduct a mechanistic analysis of reasoning behaviors in large language models, identifying distinct thinking modes and exposing inconsistencies in reinforcement learning optimized models. Their work sheds light on the internal mechanisms that drive reasoning in these models, providing valuable insights for improving performance and reliability. Another notable contribution comes from Hu and colleagues, who introduce LLMGameBench, a benchmark for evaluating how well LLMs can play video games. This benchmark requires models to demonstrate perception, memory, and planning capabilities. The common goal across these papers is creating more efficient, transparent reasoning processes, with a key innovation being the adaptive allocation of reasoning effort based on problem difficulty. The second theme focuses on neurosymbolic AI, which combines neural networks with symbolic reasoning to create more interpretable and trustworthy systems. This approach aims to leverage the strengths of both paradigms, the pattern recognition and learning capabilities of neural networks, and the explicit knowledge representation and logical reasoning of symbolic systems. One influential study by Gould and colleagues presents Gradual Abstract Argumentation for Case-Based Reasoning, a neurosymbolic classification model where outcomes are determined by an argumentation debate structure learned simultaneously with neural feature extractors. This approach provides human-aligned reasoning and improves model interpretability compared to traditional neural networks. The focus on interpretability is also evident in Radmer and colleagues' work on ClickSight, which uses large language models to interpret student click streams in digital learning environments. By analyzing patterns of interaction with educational software, ClickSight can reveal insights about learning strategies in a human-understandable format. This application demonstrates how neurosymbolic approaches can bridge the gap between raw data and meaningful interpretation, making AI systems more transparent and useful in real-world contexts like education. The third theme explores formal methods and specification-based AI, which use mathematical frameworks to specify desired behaviors and verify AI systems. These approaches provide rigorous guarantees about performance and safety, which is increasingly important as AI systems are deployed in critical applications. Kazemi and colleagues present a reinforcement learning framework that translates omega regular specifications, a formal language commonly used in verification, into average reward objectives for learning in continuing environments. This approach enables the automatic translation of behavioral specifications into rewards, avoiding the tedious and error-prone process of manual reward design. Similarly, Xu and colleagues provide a theoretical characterization of probabilities of causation with multi-valued treatments and outcomes, resolving a long-standing gap in the formal understanding of causality in decision-making systems. Their work extends Pearl's original framework for binary probabilities of causation to the more general case of multi-valued variables, providing a complete set of representative probabilities and tight bounds for their computation. This theoretical advancement has important implications for causal reasoning in AI systems, enabling more sophisticated analysis of cause-effect relationships in complex scenarios. The fourth theme combines value alignment and real-world problem-solving, focusing on creating AI systems that respect human values while tackling complex challenges. Ensuring that AI systems act in accordance with human values and preferences is a central challenge in AI research. Veris and colleagues introduce HAVA, a hybrid approach to value alignment that combines explicit representations of legal and safety norms with learned representations of social norms. This system weighs rewards based on the agent's compliance with these norms, creating a flexible framework for value-aligned behavior that can adapt to different contexts and requirements. In a related vein, Zahidi and colleagues present a computational model that infers the cognitive states of autonomous vehicle users and other road users. By integrating this information into the vehicle's decision-making process, their approach enhances well-being and trust while balancing operational costs. Qian and colleagues introduce Modeling Agent, a multi-agent framework that coordinates tool use and enables iterative self-refinement to generate well-grounded, creative solutions to interdisciplinary modeling challenges. This work demonstrates how AI systems can tackle complex, open-ended problems requiring diverse skills, from formal reasoning to domain knowledge and creative problem-solving. Now, let's explore the key findings from these papers that represent significant breakthroughs shaping the future of AI. First, Xu and colleagues provide a complete characterization of probabilities of causation with multi-valued treatments and outcomes. This resolves a decades-long theoretical gap in the understanding of causality, extending Pearl's original work on binary probabilities of causation to the more general multi-valued case. Using formal mathematical proofs, the authors derived tight bounds for a complete set of representative probabilities, creating a comprehensive framework for causal reasoning in complex scenarios. Second, Zhang and colleagues' adaptive self-recovery reasoning framework makes large reasoning models more efficient without sacrificing accuracy. By introducing accuracy-aware length reward regulation, this framework adaptively allocates reasoning effort according to problem difficulty, reducing the reasoning budget by up to 32.5% with minimal accuracy loss. Third, Kazemi and colleagues present the first model-free reinforcement learning framework that translates absolute liveness specifications to average reward objectives. This enables learning and communicating Markov decision processes without episodic resetting. Fourth, Veris and colleagues' hybrid approach to value alignment outperforms single norm methods by integrating both explicit rules and implicit norms. Finally, Qian and colleagues demonstrate that multi-agent systems can produce expert-level solutions to open-ended problems, with their modeling agent generating solutions indistinguishable from those of human experts. Across these research papers, several methodological approaches emerge as particularly effective for advancing artificial intelligence. Multi-agent frameworks for complex problem decomposition and collaboration appear frequently, allowing researchers to tackle challenges that would be difficult for single agents by dividing tasks among specialized components with different roles and capabilities. Neurosymbolic integration combining neural networks with symbolic reasoning is another common approach, leveraging the pattern recognition abilities of neural networks while maintaining the interpretability and explicit knowledge representation of symbolic systems. Formal verification techniques providing mathematical guarantees about system behavior are increasingly important, especially for safety-critical applications where reliability is essential. Many papers also explore adaptive and self-improving systems that refine their own reasoning processes based on experience or feedback, enabling more efficient and effective problem-solving. Finally, benchmarking with human evaluation to assess real-world applicability is becoming standard practice, ensuring that advances in AI research translate to meaningful improvements in practical applications. These methodological approaches represent powerful tools for addressing the current challenges in artificial intelligence research. Let's take a closer look at one of the most significant papers in our collection. Xu and colleagues' work on the complete characterization of causation probabilities. This research resolves a decades-long theoretical gap in understanding causality by extending Pearl's binary framework to multi-valued treatments and outcomes. The significance of this result cannot be overstated. Causality is fundamental to decision-making in AI systems, and this comprehensive theoretical framework enables more sophisticated reasoning about cause and effect in scenarios with multiple possible actions and outcomes. Using formal mathematical proofs, the authors derived tight bounds for computing a complete set of representative probabilities, creating a rigorous foundation for causal analysis. This advancement has wide-ranging applications across domains such as medicine, autonomous systems, and policy design. For example, in a medical context, this framework allows for reasoning about the probability that a specific dosage of a medication caused a particular level of improvement in a patient's condition. Similarly, in autonomous driving, it enables reasoning about the probability that a specific steering angle caused a particular deviation from the planned path. By providing a complete characterization of these probabilities, the authors have created a foundation for more principled and reliable causal reasoning in AI systems. Another standout paper comes from Zhang and colleagues, who introduced the adaptive self-recovery reasoning framework for making large reasoning models more efficient without sacrificing accuracy. This research addresses one of the major challenges in deploying large language models for reasoning tasks: their tendency to engage in excessive, redundant reasoning even for simple problems. The authors introduce accuracy-aware length-reward regulation, which adaptively allocates reasoning effort according to problem difficulty. This approach reduces the reasoning budget by up to 32.5% with minimal accuracy loss, representing a significant improvement in computational efficiency. What makes this result particularly significant is that it not only improves efficiency but also enhances safety, with experiments showing significant boosts in harmless rates on safety benchmarks. The ability to adaptively switch between thinking modes based on problem difficulty represents a major step forward in creating more efficient and reliable reasoning systems. This approach could lead to significant reductions in computational resources required for complex reasoning tasks, making advanced AI capabilities more accessible and sustainable. As large language models continue to grow in size and complexity, techniques like adaptive self-recovery reasoning will be crucial for ensuring they can be deployed effectively and responsibly. The third paper we'll highlight is Qian and colleagues' work on Modeling Agent, a multi-agent framework for solving complex problems. This research represents a significant advancement in AI systems' ability to tackle open-ended, real-world problems that require interdisciplinary knowledge and creative thinking. Modeling agent coordinates specialized agents with different roles and capabilities, supporting structured workflows and enabling iterative self-refinement to generate well-grounded, creative solutions to mathematical modeling challenges. What makes this result particularly groundbreaking is that modeling agent often produces solutions indistinguishable from those of human experts, as evaluated by modeling judge, an expert in the loop system leveraging large language models as domain-specialized judges. This demonstrates a level of problem-solving sophistication that goes beyond pattern matching to include creative formulation, tool selection, and solution refinement. The ability to tackle open-ended, real-world problems is a key milestone in AI development, moving beyond narrow, well-defined tasks to more general and useful applications. Modeling agent shows how multiple AI components can be orchestrated to solve complex problems that require diverse skills and knowledge, pointing the way toward more capable and versatile AI systems that can address challenges in domains such as engineering, science, and policy. Looking toward the future, several research priorities emerge from our analysis of these papers. First, developing more efficient coordination mechanisms for multi-agent systems will be crucial as AI tackles increasingly complex problems requiring collaboration between specialized components. Current approaches often struggle with communication overhead and conflict resolution as the number of agents increases, so more scalable coordination methods are needed. Second, integrating formal verification with deep learning for safer AI represents an important direction, combining the flexibility and power of neural networks with the rigorous guarantees of formal methods. Third, creating unified frameworks that combine multiple value alignment approaches will be essential for ensuring AI systems respect both explicit rules and implicit social norms across different contexts. Fourth, scaling neurosymbolic methods to more complex domains remains challenging but promising, potentially leading to AI systems that are both powerful and interpretable. Finally, establishing benchmarks that better reflect real-world problem complexity will be necessary to drive progress toward AI systems that can address practical challenges across domains. These research priorities highlight the ongoing evolution of artificial intelligence towards systems that are more capable, reliable, trustworthy, and aligned with human values and goals. A brief note on our methodology for creating this AI synthesis and review. The content for this podcast was synthesized using GPT Anthropic with model Claude 3-7 Sonnet 20250219, enabling comprehensive analysis of multiple research papers and identification of common themes and implications. Text-to-speech synthesis was performed using Google TTS technology to create the narration you're hearing now. Visual elements for the accompanying slides were generated using OpenAI's image generation tools, creating clear and informative visualizations of key concepts. Importantly, all synthesized content was reviewed by human experts for accuracy, ensuring that the technical details and research findings are correctly represented. While this review process is thorough, we acknowledge that some oversights may exist. All references to the original papers are provided for listeners who wish to explore the research in greater depth. This combination of advanced AI tools and human expertise allows us to provide timely, accessible, and accurate summaries of cutting-edge AI research. In this podcast, we bring you the latest breakthroughs in computer science and AI, straight from the archived preprint server. From neural networks to quantum computing, we simplify complex research so you can stay ahead. Whether you're a developer, researcher, or tech enthusiast, AI Frontiers keeps you informed daily. We invite you to subscribe to our YouTube channel for weekly research summaries and join our community of AI researchers, practitioners, and enthusiasts. By subscribing, you'll get early access to upcoming research synthesis episodes and can share your thoughts with fellow viewers in the comments section. Your feedback helps us improve our content and better serve the AI community. Thanks for listening. If you enjoyed this episode, subscribe for daily updates. See you tomorrow with more cutting-edge AI insights. Disclaimer. This video uses archive.org content under its API terms of use. AI Frontiers is not affiliated with or endorsed by archive.org.